In here, we would be showing that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5. For that, we will be starting from the forms of 6q and proving that the required are odd. So, a be any positive integer and b be 6, and by Euclid's division lemma, a is equal to bq plus r, in which r is greater than or equal to 0 and smaller than b. So when giving the values, a is equal to 6q plus r and r is smaller than 6, so r will have the values 0, 1, 2, 3, 4, 5. Now when r is 0, a is equal to 6q plus r, that is a is equal to 6q plus 0, that is a is 6q. Let me also explain to you that if we are able to express a value as 2m, then it is an even number, and when 2m plus 1, it is an odd number. So we are taking 2 as common just to prove that it is an odd number or an even number. You would see that we have now settled in 2m, which can be said that 6q is an even number. This is the first point. And now when r is 1, a is 6q plus 1, we are taking 2 as common, and now it is 2 into 3q plus 1, and instead of 3q we are putting m and writing it as 2m plus 1, which means that 6q plus 1 is an odd number. And now when r is 2, a is 6q plus 2, which is a is equal to 2 into 3q plus 1, and when taking 3q plus 1 as m, it is 2m. That means 6q plus 2 is an even number. This is our third statement. Again when r is 3, a is 6q plus 3. Now we are expressing 6q plus 3 in an easy way in which we can take 2 as common. And I also need you guys to study this. Now we are at 2m plus 1, which means 6q plus 3 is an odd number. And this is our fourth statement. When r is 4, a is equal to 6q plus 4, taking common, a is equal to 2 into 3q plus 2. When taken m as 3q plus 2, it is 2m at the end, which means that 6q plus 4 is an even number. And now when r is 5, a is equal to 6q plus 5. Just as before, we are expressing this as 6q plus 4 plus 1 in order to take 2 as common. That is, 6q plus 5 is an odd number with the form 2m plus 1. We have conducted this up to R5. And now from the statement 2, 4 and 6, it is clear that all odd positive integers are of the form 6q plus 1, 6q plus 3 and 6q plus 5. In here, we are supposed to find the maximum number of columns in which they can march. It is also given that the two groups are supposed to march in the same number of columns. That is, we will find HCF of 616 and 32. We are finding HCF by Euclid's division lemma, in which the larger number of the two becomes A and the smaller number becomes B. Then by Euclid's division lemma, A is equal to BQ plus R, in which R is greater than or equal to 0 but smaller than B. We would continue our steps until our R is 0. The quotient of our division will be the Q and our remainder of the division will be the R of the equation. Now to continue until R is 0, we will take our previous B as our new A and our previous R as our new B. And when R is 0, the B of the following equation will be our HCF. That is, required number of columns are 8. In here, we will use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. Now, we will consider a as any positive integer and b be 3. By Euclid's division lemma, a is equal to bq plus r, in which r is greater than or equal to 0 but smaller than b. So now we will constitute our a and b into equation and proceed. When following the condition of r, we will get 0, 1, 2 as a possible reminders of a is equal to 3q plus r. When r is 0, then a is equal to 3q plus 0, that is a is 3q. We need to show that the square of any positive integer is either of 3m or 3m plus 1. For it, we are squaring the both sides and proceeding until we get a 3m or 3m plus 1. Then look, we will see that we are taking a common from 9q square and it becomes 3 into 3q square, which we will change into 3m when m is equal to 3q plus r. This is the first statement. And when r is 1, just as before squaring both sides, now we have reached a point where the value is 3m plus 1. This is the statement 2. And now when r is 2, a is 3q plus 2. While squaring on both sides, we are expressing 4 as 3 plus 1, so it is easy to take common. So we have expressed this also as 3m plus 1. This is statement 3. So from 1, 2 and 3, the square of any positive integer is either of the form 3m or 3m plus 1.